subject name like in PRC2 we will discuss two-way slabs, columns design, design of footings, and bond and development lengths. So these topics we will cover in the theory part, and in lab portion concrete mix design, models of elasticity of concrete, some testing of columns, and non-destructive testing of concrete will be covered, and load test, discussion on load test, and core cutting method according to ASTM will be discussed, and testing of concrete cores. So first I want to show you CLOs. So let me share my screen first. So 37 students are online. Have you studied design of compression members in steel?
Yes, sir.
Good. So you will find that design of compression members in concrete is rather simple. There are less checks if you compare design with steel member design. you will find it is little easier. And so this is the course code CE411, and design of short uniaxial biaxial loaded columns, design of two-way column supported slabs, design of individual and combined footings, and to calculate development lengths and splices, and analyze and design water tanks and retaining walls. So this will also be covered, design of tanks and retaining walls. So there are 5 CLOs. So before midterm exam, we want to cover columns topic and design of two-way column supported slab. So first and second CLO, and some part of the fourth CLO to calculate development lengths and splices we want to complete till midterm, and then after midterm, the footings and the retaining walls and remaining part of the development length will be discussed. I will also upload this uh, first lecture file on MS Team. So column is a vertical member which is primarily subjected to axial compression, in which major deformation is shortening. Types of column based on shape are square columns, rectangular in geometry, circular, L-shaped, or T-shaped. So at the intersection of the walls, if you want to draw or insert a column at the corners, then both sides you may extend. So then L-shaped geometry will be more feasible. If walls are perpendicular, like if they are making a T shape, it is again more practicable to have the geometry like T-shaped in such junctions of the walls. So at corners, at the intersection of two adjacent panels, particularly when you have masonry infilling and you want to conceal the columns, then this L geometry or T geometry will be more attractive because you will be actually concealing the columns within the wall thickness. Circular, rectangular or square sections are also very much suitable to carry the axial compression. You know very well that circular section has same mode of inertia about axis, while square and rectangular, for square Ix will be equal to Iy, and at some other angle not orthogonal to x and y axis, you need to determine the I value. For rectangular section, one side will be of shorter thickness and the I value about that axis will be relatively less as compared to the one which has more thickness. So these shapes, which are very commonly used, are described on this slide. You will find that the steel is detailed symmetrically. At each corner of the cross section, one bar is present. So in square geometry, it is recommended to have minimum 4 bars, one at each corner. But you may have place more steel, but minimum requirement is 4. In rectangular, again minimum requirement is 4, and then furthermore you can put additional bars along the edges. But you will remain symmetrical in steel placement. Why it is important, that will be part of our discussion when we will discuss columns under bending. In circular columns, minimum requirement is 6 bars uniformly spaced on the circumference, and you can introduce more number of steel bars, but minimum requirement is 6. Similarly, in T or L shaped steel, at each corner is mandatory even at this position, and in this case at each corner is important because we want to detail the ties, and tie will envelop the corner bar, it will be bent around the corner bar. So important is that at the corners bars are present. In circular geometry, we may provide discrete rings like shown in this section, or the longitudinal bars may be enveloped by the spirals, helically wound continuous steel bars, spirally reinforced or spirally confined circular column. With reference to type of reinforcement in the column, this slide is important. Tied columns have the bars braced or tied at close intervals by closed loops called ties. Keep in mind this first picture, second one as well. And also, if the geometry is T or L shape, in all these pictures, there are ties present, closed loops. It is important to note that in this L-shaped geometry, there are two ties present. One is shown with the hook over here, and other is the one which is shown with the hooks over here. So there are two ties present. Even in T geometry, this one tie will envelop these 6 bars, sorry, 8 bars, 1, 2, 3, 4, 5, 6, 7, 8. And these 4 bars are further enveloped by the second tie. So this tie actually is enveloping 4 plus 4, 8, 9, 10, 10 bars. Even in this rectangular column, if it is required, we can introduce one more tie over here. We will discuss why we provide additional ties. So this diamond shaped additional tie we can provide. So it means there will be two ties at one section. So if this in circular column, it is a discrete ring, it again is a tie. But if spiral is present, then we can't classify it as a tied column, then we will call it a spiral column. So tied columns have bars braced or tied at close intervals at center to center spacing that will be defined. We are going to design that center to center distance between the ties. That will be the design goal, to design the longitudinal steel, to design the ties or spirals. So spiral columns have the bars and the core concrete wrapped with a closely spaced helix or spiral. So the word spiral means that the longitudinal bars are spiraled by the closely spaced helix. So these both tied and spiral columns is our discussion part in PRC2. So first we will design these two type of columns as short columns, axially loaded only. And then we want to discuss their design when they are subjected to bending as well. So start will be with the design of axially loaded short columns, whether they are tied or spiraled. Also are popular composite columns, which consists of a structural steel or cast iron column encased in concrete, reinforced with both longitudinal and transverse reinforcements. So this is a good picture to describe composite column. So at the core, there is a solid steel shape, maybe H section or I section. And then it is concealed by the concrete. And within the concrete, again, the longitudinal bars and the ties are present. In contrast, a ordinary reinforced concrete tied column has no such solid steel shape inside the core concrete. Then there is another popular technique which is named as pipe columns or concrete filled tubes. Although it is mentioned here steel tubes, but nowadays FRP tubes, fiber reinforced polymer tubes, are also getting popular. So pipe columns or concrete filled tube columns are circular, rectangular or square hollow sections filled with concrete without any additional reinforcement. So the casing will be used as the confining medium, steel pipe or FRP tube, and inside that concrete will be filled. So there are advantages of such pipe columns. So to decrease the demerits of steel tubed pipe columns, like in steel pipes, rusting was a major problem. So now FRP tube columns can give us a additional benefit that rusting is not a major concern when you will be dealing with a FRP tube columns. There are some demerits of FRP tube columns and some merits as well. So both type of columns are now quite popular. And in contrast, spiral column is shown here, conventionally reinforced with the longitudinal steel bars, which are spiraled around with the spiral steel. So a good confinement of the core concrete if it is spiraled as compared with the tied circular column where ties will be present discrete rings at constant interval. So in tied column, confinement is not as good as it will be in case of the spiral column. So spiral columns will have more ductility as compared with the tied columns. So pipe columns or concrete filled steel tubes are circular, rectangular or square hollow sections filled with concrete without any additional reinforcement. Now we want to discuss with reference to position of load the types of column. As I said earlier, axially loaded column or concentrically loaded column, when the resultant of the load coincides with the centroid of the cross section, column is said to be concentrically loaded. So no movement will be introduced on the cross section. However, when the resultant of the load does not coincide with the centroid of the cross section, column is said to be eccentrically loaded. So there are two types of eccentrically loaded columns. In both types, we want to discuss in this subject uniaxial as well as biaxial eccentrically loaded columns. So starting with concentrically loaded column, we want to design eccentrically loaded column as well. So in this picture, you will, you will get idea that this is rather simple design element, load applied at the centroid, while in the second and third picture, load is not concentric with the centroid of the cross section. In this picture, it is moving along x-axis and eccentricity is introduced, while in this picture it is having the location eccentric with reference to x and y axis. So it is not moving along x or y axis, but it is at some position where both the eccentricities are present, ex and ey as well. So in second picture, movement will be about y-axis only. P load and P into Ex will give us My. So we then need to design the column for P as well as My. So Ex will produce movement about y-axis. In third picture, we will have not only Ex and Ey, so we need to deal with then P as well as Mx and My. So this column will be designed, and biaxially loaded columns will be the design element. Now, in this slide, we want to discuss sources of eccentricity in column. So this picture describes three possibilities. First one is initial crookedness. So there may be a dent in the formwork, poor workmanship may introduce eccentricity due to initial crookedness in the alignment of the column, or eccentric loading, some brackets protruding outward from the columns and load applied at some distance with reference to the centroid of the column. And third one is again out of plumbness, rather having a vertical alignment, column is little out of plumb, maybe due to architectural reasons or otherwise, again lack of quality control, poor supervision, and as a result, out of plumbness may cause this additional movement. So types according to ACI 318 2019 publication in chapter 6, article 6.2.5 defines short concrete column as in short columns there are no second order effects and the failure is due to crushing of concrete without any instability. Simple to design, while a column is said to be short column if it satisfies the following conditions: that effective length factor taken from alignment charts K, unsupported length of the column LU divided by radius of gyration I over A under root. If it is less than or maximum equal to 34 plus 12 into ratio of the end moments, if column is a part of a frame structure and at ends movements are present, because column has two ends, so at end I end and J end, you can say the lower end and upper end. So if movements are present M1 over M2, you divide them and the answer you get less than the right hand side. And furthermore, if KL over R is less than or maximum equal to 40, so both should be satisfied, there is and in between, then column will be a short column. Now what about M1 over M2? It is further explained that magnitude of smaller end movement with sign will be named as M1 and magnitude of larger end movement. So you will have the frame analysis and you are knowing the end movements. Out of them, smaller you will consider as M1 with sign and larger with sign as M2. You understand very well that the ratio will be 0 when there are no end movements. Column has no built-in conditions, so there are no movement transferred, while M1 over M2 will take a negative sign for single curvature, like this is the condition, while M1 over M2 will take positive sign for reverse curvature, like this one. So you will understand that when we have a double curvature, reverse curvature, we will get positive sign in between 34 plus 12. So if M1 over M2 are equal, and furthermore the column is under reverse curvature, so you will get 34 plus 12, a bigger threshold. 34 plus 12, it will become 46, and you will get a bigger threshold to still classify your column as short column. While if column has single curvature, then 34 minus 12, and if both hand movements are equal, so the threshold to get the short column classification will be reduced. So it means then you will have 22 as the value, that if your KL over R falls below or maximum equal to 22, then column will be short column. So in concrete columns, when we want to classify them first, that whether they are short or long, this check is important. We will apply it in the design problems. If columns are long columns, also word use slender columns. So these columns fail due to buckling, instability, or second order effect. Failure load is less than that of a short column. So full material strength will not be utilized. As length of column increases, probability of failure due to buckling increases. And to classify that a column is long column or slender column, the following equation is important, as already discussed on the previous slide, that if KL over R exceeds the right hand side for single or double curvature, then you will be dealing that column as the long column. So a column is said to be short if it satisfies, as I earlier said, M1 equal to M2 and both are having single curvature. So it falls to 22 then right hand side. So less than 22 will be short and greater than 22 will be long. So it is the classification for sway permitted columns as per article 6.2.5. So lateral deformations, if they are present, are permitted. Lateral push, then you need to keep eye on this ratio, that it should be less than 22 for short or maximum equal to 22 for short, and if it is greater for sway permitted columns, then it will be a long column. Now, as we have seen some sections, and in those sections the longitudinal bars are shown with solid circles and ties are shown as well. So this longitudinal steel and the confining steel or the ties, stirrups, or the spirals. Now we want to discuss their role or significance in concrete columns. Longitudinal steel present along the length of the column is called longitudinal steel. The main function of longitudinal reinforcement is to prevent creep and shrinkage in the column. So it means if you have a calculation which supports that the load required can be handled by the concrete alone, cross section is good enough, it can take on the demand. So theoretically speaking, steel is needless because concrete alone can take that demand of axial force, but still you have to provide the longitudinal steel because concrete is prone to creep and shrinkage. So presence of longitudinal steel has a significance as it will help to prevent creep and shrinkage, and the corresponding distress in the column will be reduced. Furthermore, the longitudinal steel will also safeguard against accidental eccentricities, against lateral bending, cracking as a result of it, and reduction of moment of inertia. So absence of longitudinal steel, even though the calculations supports that concrete alone can take this axial force, will be dangerous because any accidental eccentricity or due to that eccentricity or that eccentricity, as you have seen, that initial crookedness out of plumbness may also cause appearance of movement on the column. Furthermore, in our frame construction, beams are framing in the column, so they are also transferring the movements to the column. So it is not possible to have this ideal column which has no movement. Normally movements are present, and axial, uniaxial or biaxial bending cases will be handled for short or long columns. So if just for academic discussion, we have the option of the axially loaded column and we are asked that can we go plane without reinforcement, then our answer should be that to avoid distress due to creep and shrinkage and to prevent brittle failure due to bending which may take place due to accidental eccentricities, it is important to have the longitudinal steel. And when we have the demand on the column and it is a heavy demand and concrete alone, it will be used to determine the capacity of the cross section, we may end up with a very big cross section. But the presence of steel bars in the column will provide us axial force resistance with a relatively shorter area because steel has almost 10 times more than concrete modulus of elasticity. So it will reduce the size of the column. And keep in mind that ACI code recommends that minimum 1% steel, 1% of the gross area, 1.0, 1% of the gross area steel reinforcement should be present in the column. So when your calculations tell you that you can go with 0.5 or 0.7%, so you need to round up the longitudinal steel to 1% according to ACI code. So the wisdom behind this is that it will reduce creep and shrinkage, and also it will provide the resistance against bending and sudden drop in the capacity. role of the transfer steel is also very important. It provides confinement to the inner concrete, core concrete which is present inside the longitudinal reinforcement. Confinement provides ductility and it also increases the strength of the concrete. You understand that when the material will be confined, it will have increased strength. So confinement always improves the strength of the core concrete, and it also improves the ductility. Transfer steel reduces the chances of buckling of longitudinal steel. So between tie to tie, KL over R of the bar will be reduced. So you will calculate for this bar what is KL over R. It will be reduced. Imagine that if there are no such ties, the KL over R of the bar will increase and out of plane buckling of the bar will take place. So ties are also reducing the slenderness of the longitudinal steel. It holds the longitudinal steel in position during casting, and also its major role is resistance against shear. So let me end today's lecture. So one student was waiting in the lobby, 72. CR.
Yes, sir.
So I hope next time, inshallah, we may have on-campus teaching resumed. But
Yes, sir, inshallah.
I think this week's 2 hour lecture of your section will be taken by Dr. Irfan. So in this way, next week your 2 hours lecture will be taken by me. So we are going to
Okay, sir.
swap this per week.
Okay, sir.
So okay then, Allah Hafiz. This recording will be uploaded and I will also upload this soft file.